Okay, we're sorry. Alright, so we're going to continue our discussion on functions today. So we're still in 1.1, we'll be there for a while, we'll probably be there next class as well. So it's 1.1 continue. We're going to continue talking about the domains of functions. We find the so-called domain of functions. Which, by the way, you might notice on the quiz, there was a bonus section on the quiz where I asked you, among other things, about the domain of a function. So that will be very typical from now on quizzes and on tests. I will always have a bonus section on it. And so that's where you can get extra. So technically you could have gotten more than 100% on the quiz. And what I would do is, in that case, if you get more than 100, I'll take that extra and I'll add it to another quiz. So if one of your other quizzes is bad, I'll just take the extra from this one and add it to that one. So that's how that'll work. And the bonus, how bonuses are picked is I put them on topics that I'm about to teach. So I wouldn't have done it in class yet. So for example, one of the questions was on domains. Right? So that was in the bonus section because I didn't talk about domains yet. So it's basically to reward people who are trying to read ahead and trying to get ahead of the game. You guys can actually take a shot at the bonus problems and get some extra points. So that's what that's about. But we're going to continue our discussion on functions, and it's going to be a lot of me throwing definitions at you and reminding you about stuff. But let's continue. What is the domain of a function? How would you describe it? Make sure this is. How do you describe the domain of a function?
It's the set of outputs the set of inputs of a function that will give you one output for each input. A real output. Yes. A real one.
Yeah, that's a pretty nice way of putting it, actually. So there are several ways we can describe this in words. The set of inputs for which the function is defined is one way you can put it, or makes sense, is meaningful, and as Victor said, in this class it means gives a real number output. There are things that are called complex numbers, but we won't actually do that in this class. So any value that you can plug into a function and it gives you an answer that makes sense by our estimation is, we say that it's in the domain of the function. So it's just a set of inputs that work, basically. There are two kinds of domains that we're going to be looking at. Restricted domains, so domains may be given. So I can tell you the domain of a function. So for example, I can say, okay, f of x is equal to 2x plus 3, and I can restrict you and say, oh, the x has to be between 1 and 3. Right? So in that case, this here is the domain of the function, and it's given. So while 2x plus 3 on its own can work for other values of x, I define this function to only work for these values of x. And you can say, I've given you the domain. I've given you the inputs for which I would define this to make sense. If you're not in this range, then this function is not the definition that you should be taking. It won't make sense to use them. Okay, so a domain might be given to you. But the far more important case is where the domain may be forced, depending on the nature of the function itself. And this is really talking about the case where no restriction is given and you just want to find the largest possible domain. Okay? And in general, there's no real set way to find the domain, but we're not going to be talking about all kinds of functions. In this class, we're going to be talking about very specific kinds of functions, and we do know how to find the domains of these kinds of functions. So I'm going to mention the important functions in this class, and how to find their domains, which, again, it should be a review for you. You should have seen this at some point in algebra, at the very least in pre-calculus. So in this calculus class, there are about 5 kinds of functions that we will care about and that we will study in general. Polynomials, radical functions, rational functions, exponential functions, and logarithmic functions. Exponentials and logarithmic functions we'll talk about at a later point, but right now I'm going to tell you about the first 3. Right? So the first kind of function is called a polynomial. These are functions of the form, what does a polynomial look like? Give me an example of a polynomial.
Like 2x plus 3.
2x plus 3. What I wrote down here, this was an example of a polynomial. In general, you can think of polynomials as having a form that looks like this. X to a power, some number, x to a lower power, where the ai's are constants, which we call coefficients, and n is a non-negative real number, non-negative whole number. So any function that has that form, the order doesn't matter, I can arrange these in any way I want, but any function that has that form or can be arranged to look like that, we will call a polynomial. So for example, y equals 2x plus 3 is a polynomial. Y equals x squared plus x. Y equals 5 minus 2x cubed plus 7x to the 9th, etc. These are all polynomials. Okay. Non-examples. These are not polynomials. So something like y equals x to the half plus 2x, or y equals 3 plus x squared minus 5x minus 1. These are not polynomials. Okay? Why is this not a polynomial? Yeah?
Because you have an exponent of 1/2 and not a whole number.
Half, right? By our definition, to be a polynomial, you can only take on non-negative powers, whole number powers. So you can be 0, or 1, or 2, or 3, or 4, or 5. And this is not a polynomial. Why? Yeah?
This is a negative.
Because this is negative exponent. Okay. So that's not a polynomial. Now it turns out we know what the domains of polynomials are. What's the domain of a polynomial? Give you a random polynomial, I don't get a restriction, what is its domain?
All real numbers.
All real numbers. I can literally plug in anything and it will work in a polynomial. This is to say all real numbers, or this is to say any x that's between infinity and minus infinity, which is everything, can work here. So all real numbers. So I can literally plug in any number on the number line into these guys and they will actually give me a meaningful answer. They will output a real number. However, in this one, that is not the case, you may have noticed. I cannot actually plug in a negative x. If I plug in x equals -4, this makes no sense for our purposes. This one, I cannot plug in 0 for x, right? Because here I have 1 over x, I would divide by 0. That doesn't make sense no matter what level of math you're talking about, right? So these guys have restrictions. There are numbers I cannot plug into them. However, these guys, I can literally plug in anything on the number line and they will work. Polynomials are very nice functions because their domain is everywhere. They work everywhere on the entire real line. Which is why, I don't know if any of you might switch in the future to something that needs a lot more math. When you go to Calc 3, you'll learn about things called power series, which is basically you try to write functions that are not polynomials to look like polynomials, and sometimes this takes an infinite number of terms, but the trade-off is worth it because polynomials are so nice, they're very well behaved, and in terms of calculus, they're very nice functions to do calculus with. Okay? So their domain is literally everything. There's another kind of function though that can have restriction. These are called radical functions. These are functions of the form something that looks like y is equal to the nth root of x, or similar. Underneath here, you don't have to have an x, you can have some general function. That's called a radical function. So, example, like y equals square root of x, y equals cube root of x, y equals x to the 2/3, etc. These are all radical functions. Basically, in a polynomial, you allow the functions, the powers to be fractions instead of whole numbers.
Just a quick question. So for x is x to the 2/3, could you write that as the cube root of x squared?
Yes. So this is a fancy way of writing, or well, with the radical is the fancy way I would say. So that's actually the same, right? So if you have fractions, non-whole number fractions, that gives rise to radicals. You can always rewrite that. And when I talk about exponential functions, I'll remind you about things like this, laws of exponents and how these work. But these are all examples of radicals. What about the domains of radicals? How do you find the domain of a radical function? Yeah?
Is it like greater than, or you could do like 0 or something?
Greater than or equal to 0?
Or like greater than
Is that
0?
true? Yeah?
Oh, it would depend on which radical, right?
In what sense?
Because if you had the square root of x, it would be 0 to, it would have to be 0 and greater than 0, because
Okay.
you can't take the square root of negative.
Okay.
But if it's an odd root, then you could have a negative number, because -1 times -1 times -1 is 1.
Okay, so give me a rule. The domain of the nth root of x would be, there are two cases, is what I'm hearing you say. And so what's the first case?
If n is even,
If n is even, what happens?
it's 0 to.
So it's 0 inclusive and anything bigger if your n is even. And what about if n is odd?
In negative, infinity, positive.
Everything. So the domain of such functions, it depends on the little number that's in front of here. If the number on the radical is an even number, it will only work if what's underneath the radical is 0 or bigger. If your number on the radical is an odd number though, it can work for anything, both negatives and positives. And so that would be our domain for radical functions. And of course, if a number is not written, it means there's a 2 there. There's an invisible 2. And we'll talk a little bit more about what that means later when we talk about exponential functions, but and we'll go over the rules for radicals and all that. But for now, I just want you to know about this form, this notation that we're writing down. A third kind of function, very important kind of function, is still called rational functions. What are rational functions? What's a rational function? Yep.
Is it a polynomial fraction?
Polynomial fraction, right. So rational function, though they sit around and think all day and they're very considerate, it means that it comes from the root word here is actually ratio, right? So you're taking a ratio of polynomials, you call that a rational function. So these are functions of the form p of x divided by q of x, where p and q are polynomials. functions like that, we call them rational functions. What about the domain of rational functions? Yeah.
Any number where any number x such that q is unequal to 0.
Right, so the domain of p of x over q of x is the set of all reals so that you cannot divide by 0. Q of x is not equal to 0. So in general, q here, of course, denotes the denominator. A denominator cannot be equal to 0. We have to avoid division by 0 at all costs. So anything that has a fraction, you always have to worry about whether the denominator is 0 or not. And that is going to be the domain. So basically, you figure out where the denominator is 0, and then you say the domain is everything except that. Okay, so that's how you find the domain of something like a rational function. Let's actually do some examples, make sure we know what we're talking about here. So those are 3 of the main 5 types of functions we will be talking about in this class: polynomials, radicals, and rational functions. The other 2, exponential functions and logarithmic functions, we'll talk about those later. But for now, find the domains of these. A. I didn't have this book. Let's make that last example the example I put on the quiz. So on the quiz, I asked you to find the domain of 4 over the radical of x squared minus 9. So let's see what the answer was supposed to be. A, what's the domain? Yeah?
Can't be equal to -2. Select everything but -2.
Okay, how do you write that down? Let's say we want to use interval notation, which is going to be the most common way that we want to write a domain in this class. So on the domain of g of x, and we know we cannot be -2, how do you know that? You set the denominator equal to 0, this means that x plus 2 is equal to 0, so your x is equal to -2. So we want, actually x cannot be -2. How do you actually write that down? Yeah?
Sorry, negative infinity, comma, -2, and then, wait, oh wait, no, sorry, yeah, and then -2 to infinity.
Okay. So, at least in the beginning, especially if you don't remember much of this, I'd always like to draw a picture. It'll help you to keep things on track. So you know, here's a number, this is just representing a number line. And -2, there's a hole there because I can't touch it, but I can touch every other number. And And so I want to describe each interval of numbers that I can touch. So I can touch here from -2 going all the way back to -infinity, and we write that as -infinity, comma 2. Union, or anything to the right of -2, so from -2 to infinity. Comments on this notation. Parentheses means
It doesn't include that.
it does not include that value, right? So when I put -2 parentheses, it means -2 cannot be a value plugged in, but anything as close to -2 as possible is okay. So right up to -2, but not including -2, is in the domain of this function. And this is how you'd write it in interval notation. Saying anything except -2 is saying this. And the picture would help you out doing that. So you're just writing down the intervals that describe the shaded part of the line. What about B? What's the domain of that function?
You gave it to us.
Okay, so
It's two bracket 2, comma 7 bracket.
right, why this is given. Right, so you have to be careful of that. So by itself, this was not included, works for all real numbers because this is a polynomial. However, I told you that this only works between 2 and 7, and outside of that we don't know. So 2 is included, 7 is included, and everything in between, but otherwise it's undefined. I never told you what the other part was. C. Okay, let's talk about the domain of H. How would I find that domain? Yeah.
Would you set x squared minus 9 to 0 and then you like
So set x squared minus 9 equals 0.
and then you solve it. You get
How do you solve it?
you break into x minus 3 and x plus 3.
Okay. You factor, because difference of squares, and so you'll have x equals 3 or x equals minus 3. Then we do the same thing. Here's our number line. There are two values we want to avoid because that's where the denominator is 0, minus 3, and positive 3. However, we can be everything else. And so we write down each of these groups of numbers. So we can be from -infinity to -3, not including -3, so I write parentheses, or we can be in the middle between -3 and 3, or we can be on the outside, 3 and bigger. And so there are 3 sets of intervals for this function. It's worthy to note that there are other ways to solve this. You could have had x squared minus 9 equals 0, add 9 to both sides, and then you take the square root of both sides, and you get x equals plus or minus square root of 9, which is plus or minus 3. However, this is the preferred method. It'll help you avoid confusion for later things, as well as this is a method that you can solve more general equations on. So even if it was not the difference of squares, you can solve most polynomial equations by bringing everything to one side, setting it equals 0, factoring the left side, and setting each factor equals 0. That's a general method. And this is a very specific method. This only works if you have 2 terms specifically, and one of them is a number. Okay, this will work in far more general cases. I prefer that you solve it that way. And so we'll end up with this as the answer, and now we move on. We're going to do the domain of P. So how do you do the domain of that function? It's not quite a rational function, but it has some sort of rational influence.
have to find not only where the denominator isn't 0, but you have to find where that radical is also not negative.
Okay. So in this case, we're mixing and matching functions. I have a rational function, but I threw a radical function in it. Each of these kinds of functions have their own restrictions, so you basically have to deal with one restriction at a time. Okay, so notice here there are two restrictions. First of all, there's the radical of x. Right now, what restriction that causes is that your x must be greater than or equal to 0 for that to work, because it's an even radical. 2, we have x squared minus 9 in the denominator. So that gives us another thing that we have to worry about. X squared minus 9 cannot equal to 0. So there are two things we have to worry about now. And the best way to do that is to worry about one at a time. And then talk about the overlap. So what do you think the answer would be here? Yeah?
So if we use example C, we can find the overlap once you add in the interval that would be like bracket 0 to positive infinity. So it would be bracket 0 to 3, and then a parentheses, union, parentheses 3 to positive infinity.
Yep, so that's what we're going to do. And I'll draw the picture so you can see, so you won't, it'll help you from getting confused. So basically, this tells you about the important numbers that you're going to want to check, right? So the important numbers are, for this one, it's at x equals 0, that's where the cutoff is. For this one, it's at x equals plus or minus 3. So you mark all of those in, minus 3, 0, 3. And then you're going to draw both restrictions on it. So let's say I wanted the radical that can start at 0. So you shade that to denote that you can be equal to 0, and anything bigger. So you draw that. Then you go one level up and write down the next restriction. So this one can not work at 3 or minus 3, but anything else. And so the domain of the entire function overall is simply the overlapping of the domains of these individual restrictions. So we need to find regions where both of these lines are present at the same time. So that'll give us in between here and in between here. Over here it doesn't work because only one of the functions will work there. Over here it doesn't work because only one of the functions will work there. But it seems that here, 0 up to 3, not including 3, and then everything afterwards, union 3 to infinity. Whoa. And that's how you figure out the domain. So if you have several of these types of functions mixed together, just look at each one individually, see what their restrictions are, and then do an overlapping diagram. Look for where both functions are present at the same time. And so that would be the domain. How about the quiz? The domain of 4 over the radical of x squared minus 9. Yeah.
Is it all real numbers? So it would be like from negative infinity to positive infinity?
Nope. How would you figure that out? Yeah.
Well, it's kind of like the last one, except the top doesn't have a restriction, so
Okay, so the top has no restriction,
so
but
we just focus on the bottom. And the
Okay.
domain of the bottom is from negative infinity to negative 3, and then from 3 to positive infinity. Soft brackets, because you can't have.
well, why don't we have here?
Because if you
You said it was like the last one.
because in the middle of those two it'll be negative. Inside the radical will be negative.
Okay. Well, how do you know that?
Well, less than plus or minus, well, in between negative 3 and positive 3, when you subtract it from that squared term, then you'll have a negative number.
So you just saw that, or did you solve for it?
I just saw it.
Okay.
I mean-
So, I mean, in general, things can be more difficult, but we're going to do, it's going to be sort of a combination between these two, right? There are several restrictions here. So in one case, there is a denominator, so we don't want that denominator to be 0. But in the other case, there's also a radical, so we need what's under that radical to be positive. So again, we have two restrictions here as well. Restrictions. And we'll deal with one at a time. So one, there's a denominator. Which means that your x squared minus 9 cannot be 0. 2, there's a radical. Which means your x squared minus 9 must be greater than or equal to 0. This means, overall, what you want is for your x squared minus 9 to be strictly greater than 0. Okay, so that's the first thing you need to figure out. Okay? So it can't be 0, and it has to be greater than or equal to 0, so that means we don't want the 0, but we want the bigger. Right? So finding the domain of this function amounts to solving this inequality. Now how do we solve that inequality? Yeah.
Well, you would add 9 to the right side. And you get x squared is greater than 9. And you take the square root of both sides.
Okay. So it's greater than plus or minus 3.
Yep.
Oh,
That doesn't make sense. You have to split them.
You have to split.
Can we
Yeah.
just factor it into x plus 3 and x minus 3 and then set each one to like greater than 0?
Okay. So when we have to deal with an inequality, we start by pretending there's, so to solve this, you first consider this, right? Consider where it's equal to 0. So we'd solve that in the same way. And here you're going to see another reason why it's nicer to factor as opposed to bringing things to one side. Okay? So you know, again, here you got 3 and minus 3. What do you do with those numbers? Then you put them on a number line. So before, when you're solving an inequality, you treat it as if it was an equation, and then you solve it that way. But then for the inequality, there's an extra step. You want to figure out where this is positive, where it's greater than 0. How you would do that is you test the numbers in each interval. Okay, so once you're solving an inequality and you find the numbers for the equal sign, you need to test numbers on the inside. And it doesn't matter which numbers you pick, so you pick things that are easy to do. For example, test a minus 4, test a 0, test a positive 4. Okay. And what you want to do is you want to plug into this expression and see, does it give me a positive number or a negative? Okay. And we want the positive number. Okay? So for example, if I plug in a minus 4 into this expression, it's much easier to plug it into the factored expression because you can see the sign right away. You don't care about the value, you care about the sign that is greater than or equal to 0. So if I plug in a negative 4 here, minus 4 minus 3 is negative, right? So that would be a negative. Plug in negative 4 here, minus 4 plus 3 is also negative. So you have a negative times a negative, which gives you a positive, and so this works. Plug in a 0. Here, you'll get a negative. Here, you'll get a positive. Negative times positive is negative, and that does not. Plug in a positive 4. Here, you get a positive number. Plug in a positive 4 here, you get a positive number. Positive times positive is positive, and so that works. And so for this one, it's the outer ones that work. And so the domain here, from negative infinity to negative 3, union from 3 to infinity. Any questions on that? There's another way you can look at these, and where you can know that that was, you can know even quicker that that was going to be the answer. You can't always see this for in general, but for this particular kind of expression, it was easy. And basically what you could do is use the graph. what does x squared minus 9 look like? Okay. Yeah?
Do you go down 9?
But what is the main shape?
I just kind of look like
It's a parabola, right? Going down 9. You know that it crosses at 3 and minus 3, right? So if you knew that graph, you can immediately see on the outer edges is where the graph is positive. In the middle is where the graph is negative, right? So if I see, oh, where's x squared minus 9 greater than or equal to 0? I have the picture in my head. Oh, I know it's on the outsides of the intercepts, right? So you can get to this answer like right away, okay? And if someone, for example, asks you, oh, g of x is 4 over the square root of 9 minus x squared, I would know the domain there is minus 3 to 3 because of exactly the same reason. That guy looks like this, the positive side is in the middle, okay? So knowing the graph can also help you avoid some computation, but in general, this is how you do a computation. So if you need an inequality, pretend it's an equal sign, solve for the numbers, and then test the values in the middle. It's much easier to know the signs if you factor it first. It'll be easy to see what signs function. Piecewise functions. Another important kind of function is called a piecewise function. Can you describe to me what a piecewise function is? Yeah?
A function that isn't continuous, it stops and starts.
Not necessarily. Technically, that's incorrect. You can have a piecewise function that is continuous. But what do you mean it stops and starts?
One formula does not describe the entire graph.
Okay, so it's a function in which it can have several definitions depending on the interval you're on. Okay, so these are functions that have different definitions depending on the interval being considered. So we spoke about functions as being models for relationships that connect two groups of things in a special way. What a piecewise function models is a relationship that depends on context. It's not always the same rule. It depends on what time it is, or where it is, or the context that you're in. And you can actually look at a situation like that, and if you can describe it mathematically, you'll be described as a piecewise function. Right? So it's where the definition or the rule that connects these two groups changes depending on where you are. Okay, so for example, say that f of x was equal to 1, x is between 0 and 1, it's x plus 1, and x is greater than 1. This is an example of a piecewise function, and this is pretty common notation. You write a squiggly bracket, and then on line by line, you can have write the definition for the function. So this function has two pieces. Okay, so there's one piece here, there's one piece there, and it's defined based on certain regions of the x-axis. Okay. So let's see if we all understand what this means. Let's try a couple values. Okay, so for example, evaluate f of 0.5. F of 3 over 4. F of 20. Okay, what is f of 0.5? Yeah, 1. How do you know that?
Because 0.5 is between 0 and for that 0 less than x less than 1, so you know it has to be 1.
Okay, so yeah. So here we have a function called f. The input is 0.5. If f is a piecewise function, I have to first check that 0.5 is in the domain, and then I have to figure out which one of these intervals does it fall into. A half, 0.5 is a half. A half is between 0 and 1, which means I'm looking at the first line as the definition of the function, and I ignore the second line, right? Because you can only have one definition at a time. And so if I'm between 0 and 1, the output is going to be 1 all the time, therefore that is 1. What is f of 3 over 4? Yeah,
1.
it's also 1. For exactly the same reason. 3 over 4, 0.75 is 3/4. That's a number between 0 and 1. So if the input is between 0 and 1, the function outputs 1. What is f of 20? Yeah? 21, right? Because we're doing 20 plus 1, which is 21. Why? Because if my xi is 20, it's no longer in this interval, it's now in this interval. If it's in that interval, this is the definition of the function. I ignore the first line, and then this guy is going to be x plus 1, so that's 20 plus 1, 21. What is f of minus 1?
Undefined.
Undefined. Plugging in minus 1 does not make sense in our function because I tell you that it makes sense if you're 0 between 0 and 1 or larger than 1. I make no definition for negative numbers, therefore if you try to plug a negative number in this function, it doesn't make sense. It's not meaningful because it only has meaning on these intervals. So you would say your function is undefined. How do you graph a piecewise function? So here's the thing. To graph a piecewise function, you have to first be very good at graphing in general because you have to know how to graph the pieces of the function separately, and then you kind of stitch them together based on the region they're in. So notice that this function here has two definitions. It's either the function y equals 1, or it's the function y equals x plus 1. To be able to draw the graph of this, I have to be able to draw the graph of each of these individually. Okay? What does y equals 1 look like?
Straight line.
Horizontal line going through 1. Y equals x plus 1 is also a straight line, but how does that look? Or not like this. With y-intercept 1. Right? So I have to know how to graph each of these individually. Now what I do in a piecewise function is afterwards I look at the restriction. So this one works between 0 and 1, so it only works when my x is between 0 and 1. So I know here and here it will work. And I would ignore everything outside of that range. Just ignore it, it doesn't matter. Similarly here, this one works for strictly bigger than 1, so I identify 1, create a hole, and I care about this side, and I ignore that side. Notice that at this point, my y value would be 2, right? And so for a piecewise function, what you do now is you draw both of these on the same axis. So in one case, there's a horizontal line between 0 and 1 at the level 1. So I only draw this part of the function because it's defined for only that part. Then for 1 and bigger, I will draw this picture. So there's a jump here that starts at 2 and goes there. So that would be the graph of this function. It has two pieces. Sure, they disconnect. Overall, it's not continuous, but I could have defined this so that these two connected. There would be nothing wrong with that. So yeah, to graph a piecewise function, you graph each piece in the region where it's supposed to be. To know where your function begins, you use the endpoints as your guide. So you literally plug in the endpoint into this to know that it should start at roughly at 2 and then continue and so on and so forth. We'll stop there for today. I think we're out of time. We're still not quite done with 1.1, so homework isn't due. I'll see you Friday and we'll continue with this. And we'll finish 1.1 on Friday.
The homework will be due.
And so I finished 1.1 on Friday, the homework will be due on Tuesday.